How do we move stuff around inside a factory? Well, it's easy. You just lay a magnetic stripe down between the storage and a worker in the assembly line and tell the robot to just follow the stripe. This technology relies on automated guided vehicles. But what if the piece I need is somewhere else in the factory, like here for example? What if I need it in a different zone of the assembly line? To be able to answer to the demand in the line, as well as more efficiently handle the flow of materials, a fleet of autonomous mobile robots should be deployed. Sounds simple enough, but how do we do this? First, we have to understand what is an MPC, an advanced model-based control technique for the feedback control of a nonlinear system subject to a set of constraints. This control technique has an optimization problem at its core, which is optimized over a prediction horizon, N. So, we have to describe the trajectory tracking problem and then find a way to incorporate the obstacle avoidance capabilities. We do this by describing the problem in this way. Let's break it down. The cost function describes the performance we want to optimize. In this case, A penalizes the distance to reference and B penalizes the successive control to reduce oscillations. The constraints define the feasible region for solutions. In this case, we start with the initial condition. We also have the vehicle's constraints, a differential drive vehicle given by its kinematic model. The experimental motors also have values under which they are unresponsive, and values over which it is not safe for their operation. Finally, the obstacle avoidance constraints. Let's see how they are defined. When the robot scans its surroundings or environment, it creates an occupancy map, composed of cells with a value that represents the probability that that cell is occupied. This map is too large. It must be reduced. First, only the obstacle barriers are considered. Then, we can reduce the view window of the robot considering its heading angle, like so. Finally, the occupied cells are calculated as obstacle positions and bundled by overlaying a voxel grid. The voxel cell midpoints are now the obstacles, and the robot needs to keep a safety distance from each obstacle. Let's see how well this works. First, we test the vehicle model. Is it accurate? As it turns out, there is great discrepancy between the actual robot's behavior and what the model expects it to do. That's not very promising. But as it turns out, when testing the controller in a real-world scenario, it is able to outperform the tracking of tab, which is the state-of-the-art of the ROS navigation package. It is more accurate and has less oscillations. Further, it is robust to the model errors and capable of precise tracking when tested in these conditions. The controller is also robust to discontinuities, as it is able to converge back to the reference trajectory when starting at a random initial position. Now for the obstacle avoidance. The robot is tested for different shapes of static obstacles and is able to deviate from them. More uniquely, it is able to do so while needing no a priori knowledge of the obstacle's position, shape, or dimension. The performance we see for the controller is comparable to that of tab, though tab has a tighter safety distance. Testing for moving obstacles shows that the performance between tab and the controller is comparable for when an obstacle crosses the robot's way. Finally, this work developed a controller capable of accurate trajectory tracking with integrated obstacle avoidance capabilities. This controller is robust to model errors and fit for real-world implementation, outperforming the state-of-the-art tab in these cases. Further, it needs no a priori knowledge of the obstacle's position, shape, dimension, or trajectory in order to successfully deviate from them.